Let's examine circular motion within an applied context. Suppose Kristen boards a Ferris wheel at the 3 o'clock position and rides the Ferris wheel for one full rotation. The Ferris wheel has a radius of 8 meters, and the center of the Ferris wheel is 12 meters above the ground. We will let theta represent the number of radians Kristen has swept out since the start of the ride, and we'll let v represent Kristen's height above the ground in meters. Now, like normal, we should start by drawing a diagram to make sense of the scenario. So we've got a Ferris wheel. I'll start by drawing the ground. So we've got the ground here. Now our Ferris wheel is 12 meters above the ground. So we've got the legs of the Ferris wheel, and its height, the center of the Ferris wheel, is 12 meters above the ground. And then the Ferris wheel itself has a radius of 8 meters. So pretend like that's a circle that I just drew. It has a radius of 8 meters. Kristen starts at the 3 o'clock position, so we'll draw an initial ray like that, and then she travels in the counterclockwise direction, sweeping out theta radians. So this, we're imagining this as varying, so kind of imagine that terminal ray sweeping in the counterclockwise direction, but we can only draw one instance of it. So we'll just draw a little diagram like this, and Kristen sits right here after sweeping out theta radians. So the variable v, Kristen's height above the ground, is actually a height. Right now it looks something like this. It's the height above the ground and not the height above the center of the Ferris wheel. So we know the highest she can get above the ground is up here when she hits the top, and that height above the ground is actually the 12 meters where the center of the Ferris wheel sits, plus an additional 8 meters for the radius of the Ferris wheel. So the highest she can get is 20 meters. So the highest she can get is 20 meters, and the lowest the Ferris wheel is actually 4 meters. It's the 12 meters of the center, and then take away 8 meters for the radius of that Ferris wheel. So let's start by drawing a graph that shows how theta and v vary together. So what we'll do is draw a set of axes, something like this. We'll represent theta on our horizontal axis, and then we'll represent v on our vertical axis. And Kristen makes one full rotation around the Ferris wheel, so theta, we're just imagining theta varying from 0 to 2 pi. So we can end at 2 pi over here, and then we'll split this up into a few separate intervals. So we'll split it into 4 pieces. Okay, so v will start at 0, but the largest v can get in this context is 20. So we'll put 20 up here. So 20 is right there. And the lowest Kristen gets is actually 4 meters above the ground. And then the center of the Ferris wheel is 12 meters above the ground. So if theta varies from 0, which is right there, to pi over 2, which is right there, Kristen travels along this little arc right there. And her initial height above the ground is 12 meters. And then it increases up to 20 meters. So as theta increases from 0 to pi over 2, v increases from 12 to 20. So the first part of our graph looks something like that. Then, as theta increases from pi over 2 to pi, Kristen travels along that arc. Her initial height above the ground is 20 meters, and then it decreases back down to 12 meters above the ground. So on our graph, as theta increases from pi over 2 to pi, that value of v decreases from 20 back down to 12. Then, as theta increases from pi to 3 pi over 2, Kristen travels along this arc. Her initial height above the ground is 12 meters, and then her height above the ground decreases until she hits a height of 4 meters above the ground. So as theta increases from pi to 3 pi over 2, the value of v decreases from 12 to 4. So this part of the graph looks something like that. And then, as theta increases from 3 pi over 2 back to pi, Kristen's height above the ground starts at 4 meters and then increases back up to 12 meters. So on the graph, that would look something like this. So if we fill this in, we'll just do one color, the graph of v in terms of theta looks something like this. And this matches up with our thinking of how v and theta vary together within our diagram. So this graph relating v and theta gives us a visual way of thinking about how theta and v vary together, But our graph is a little bit rough, and it doesn't actually allow us to determine exact values of v if we know a value of theta. To do that kind of work, we need a formula expressing v in terms of theta. Let's start again by drawing a diagram. Now, if we want to model Kristen's height above the ground, and we think of height, we should probably have the sine function pop into our head, as the sine function gives us a height above the center of our rotation, given a number of radians swept out. So in this case, Kristen is some distance above the center of this rotation, or above the center of the Ferris wheel, and that distance is actually sine of theta radii. However, we're trying to model Kristen's height above the ground in meters. So her height above the center of the Ferris wheel is actually 8, the radius of the Ferris wheel, times sine of theta meters. So our distance above the center of the Ferris wheel is 8 times sine of theta meters. We can visualize this by this red vector I have drawn here. However, we want our height above the ground, so we're not quite done yet. We know that the center of the Ferris wheel is 12 kilometers above the ground, and then Kristen is an additional 8 times sine of theta meters above that. So if we want her distance above the ground, we need to combine this original distance, 12, plus however many meters she is above the center of the Ferris wheel. So plus our 8 times sine of theta. So in this case, v, her distance above the ground, is equal to 12 plus 8 times sine of theta, where 12 is the initial distance above the ground, or the distance above the ground for the center of the Ferris wheel. Sine of theta represents Kristen's height above the center of the Ferris wheel in radii, and then 8 times sine of theta gives Kristen's height above the center of the Ferris wheel in meters.